to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science and technology. But in this hour, we're going to take your listener phone calls. Okay, well, let's move on now to the first listener phone call.
My name is Shirley. The last name is Critchy. The call letters of the radio station I listen to is KONA. The city I'm calling from is West Richland, Washington. My question, has the question, why is there more matter than antimatter, been answered? I would like to know if the answer may be connected to the gravity of black holes and matter which comes out white on the other side, unless the negative energy is too great and the hole explodes. Thank you.
Wow, what a question. Well, let's break it down because you're asking something that is at the cutting edge of science, and you're asking questions that the correct answer is, well, we physicists don't know. So let's break it down one by one. First of all, there is matter, of course, matter which makes up our world, the earth, the sun, the stars, matter. But there's also antimatter, which is the opposite of ordinary matter. When the two come in contact, they annihilate, like, for example, in an atomic bomb. So you don't want to get too close to something made out of antimatter. Antimatter has the opposite charge of matter, so the antiproton has a negative charge, which is the opposite of what we learn in high school. The electron normally has a negative charge, but the anti-electron has a positive charge. So, therefore, you can create anti-atoms. In fact, we've done that. At CERN, outside Geneva, Switzerland, we have this gigantic atom smasher costing over $10 billion. And that atom smasher has created beams of pure antimatter. And when you combine antimatter with other forms of antimatter, you get anti-atoms. And believe it or not, we have created anti-hydrogen. That is, an anti-electron circulating an anti-proton. Now, you ask a very embarrassing question to a physicist. By rights, we think that at the Big Bang, the beginning of the universe, everything was symmetrical in our equations. Therefore, we should have had an equal amount of matter and antimatter. And, of course, they annihilate each other. So in some sense, we shouldn't be here. I repeat, we shouldn't be here because by rights, an equal amount of matter and antimatter at the beginning of the universe should have annihilated into a bunch of gamma rays, and we should not be here. And so the first embarrassing question is, why are we here at all? Well, let's actually measure the amount of antimatter in the universe. Using our satellites, we can detect the fingerprint of antimatter. When antimatter collides with matter, it creates gamma rays of 1.02 million electron volts, and that's a signature, the fingerprint of the presence of antimatter in outer space. So when we scan the heavens, what do we find? Almost nothing. Almost nothing at that energy. In other words, sorry to say, the universe really is made out of matter, not equal amounts of matter and antimatter. And that is a mystery. What's the answer? We don't know. In fact, there's a Nobel Prize waiting for somebody that figures out why we exist at all, why there is more matter than antimatter, and thank God that's true. Otherwise, we wouldn't be here. Our atoms would have annihilated and burst into energy billions of years ago, and the Big Bang, in some sense, would have been a dud. Now, the leading theory of all this is called string theory, which is what I do for a living. And even in string theory, you have to sort of put it in by hand and fudge it a bit. So even string theory, which is the leading theory for the ultimate theory of everything, it's not quite clear why we have this problem. Now, if you want to Google this problem, go to the website of the American Physical Society, or simply Google matter antimatter annihilation or the CPT theorem and CP violation. Google CP violation and you'll get all the scientific papers that theorize about what might be causing it, but the bottom line is we are clueless. Now, the listener had a rather ingenious way of resolving the crisis. Let's say we have matter plunging into a black hole. Where does it go? We don't know. That's another big question. But some people think maybe it's blown out the other end as a white hole. And then the question that she asked was, if matter disappears into a black hole and perhaps wind up someplace else as a white hole, can that cause the difference between matter and antimatter? Well, actually, that question we can answer, and the answer is no. It turns out that objects falling into black holes obey the usual laws of quantum mechanics, and therefore, if you have an atom that goes into a black hole, it remains an atom. It does not turn into an anti-atom. And so, once again, to sum up, the answer to the question that was asked is, we physicists don't know, but here's a suggestion. If you ever figure out the reason why there is more matter than antimatter in the universe, tell me first. And we too will split the Nobel Prize money together. We too will become millionaires, winning the Nobel Prize and having our names carved in stone. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. You know, one time I was doing a book tour, and I passed through the Midwest, and a guy comes up to me and says, Professor, you really have to answer my question. And I thought, well, that's a rather strange thing to say. Why do I have to answer this question? And then he said something rather interesting, which caught me by surprise. He said, well, if you don't answer this question, I may have to wait another 10, 20 years before a theoretical physicist passes through my neck of the woods. And so please answer it now so I don't have to wait a few decades for the next answer. And I realized that, well, he was right. I mean, unfortunately, we professional physicists almost never interact with the public. That's right. We tend to keep to ourselves because, well, most of us think it's a bother answering questions from the public because they're uneducated, they're dumb, whatever. And so, unfortunately, many people, their questions are never answered. Well, this is the chance where you can get to the phones and make it right. Okay, let's move on now to the next listener phone call.
Hey, Dr. Kaku. My name is Eddie Bryant. I'm calling from Murphy, North Carolina. I'm listening to you from your website. And my question is this. I've heard Neil deGrasse Tyson say that if he could travel to another universe, he would avoid doing so because on arrival, the laws of that universe could be different and he could just turn to a blob of goo upon arrival. Now, my question regarding that is the theoretical graviton particle and now believe that it can traverse the strings no problem because it is of a size that allows it to do so. But if the graviton particle doesn't follow different rules on different universes, does that mean at some kind of quantum scale that everything behaves the same in all universes? Or does the graviton particle possibly operate different in a different universe? Thank you.
Well, you ask a question which is at the cutting edge of physics, but let me give you a straight answer. First of all, the theory you're talking about is the multiverse theory, and there are different variations of the multiverse theory. The leading variation is called inflation, where there was a supercharged inflation at the beginning of the universe, much faster than the conventional Big Bang. And because it's a quantum theory, it happens again and again and again. In quantum mechanics, if something happens, there's a certain probability that it'll happen again and again. So if the Big Bang obeys quantum mechanics, then it means that Big Bangs are happening all the time. Baby universes are fissioning off from our parent universe. So think of our universe as a big, gigantic soap bubble, and baby soap bubbles keep fissioning off, creating baby universes. And then the question you ask is, well, What happens if I enter one of these baby universes? Well, of course, in science fiction, we always like to dream that we can enter another universe where things are upside down, backwards, and crazy, and that makes for a lot of good plot lines. But as my friend Neil Tyson has pointed out, there's also a probability that the laws of physics are different in these other universes. For example, the proton may not be stable in these other universes, in which case a proton decays into a bunch of anti-electrons and neutrinos, in which case your body turns into dust. Your body will disintegrate, turn into a dust of subatomic particles, because stable matter depends upon stable protons. Our universe depends on having protons which are stable for trillions of years, or else we have no stars. And no stars means no life. However, I should also point out that there's also a probability that there are other universes where things are just like our universe. Protons are stable. They have DNA, just like our DNA. And they have people, perhaps, just like ours, except maybe a twist. Maybe you went to a different college, entered a different occupation, married a different spouse, or maybe you have a twin brother or twin sister, or maybe you don't even exist at all. In fact, your mind goes crazy thinking about all possible quantum universes that can exist in the multiverse. And so this is the stuff of science fiction. The only difference is that we physicists are now taking all these bizarre cockamamie ideas very seriously. And if you don't believe me, just Google the word multiverse, and you'll see all the good papers as well as crazy papers that are being introduced because of the fact that once you quantize the Big Bang, that is, once you apply quantum mechanics or atomic physics to the Big Bang, you have multiple universes. And then you ask yet another question, and that is about the graviton, and whether the graviton would have different properties. And the answer is no. First of all, we have Einstein's theory of gravity, which says that space-time is like a trampoline net. You can bend it, squeeze it, stretch it, compress it. So the fabric of space and time is stretchable. However, there are ripples along the fabric of space-time, and these ripples are particle-like, and they're called gravitons. For example, look at the particle of light. The particle of light is a photon. A photon is a particle of light. Whenever I watch Star Trek, I kind of giggle to myself whenever Captain Kirk says, fire the photon torpedoes, because what is a photon torpedo? A photon torpedo is a flashlight. That's all it is. So there they are turning on their flashlights trying to battle the Klingons. Well, gravity also has tiny particles associated with it, and they're called gravitons. But yeah, gravitons can go between universes. We believe that. But when they go between universes, they don't change. Atoms may change. That is, a proton may become unstable going through a wormhole. And in that situation, your universe becomes unstable and you disintegrate. However, gravitons are particles of gravity, and therefore they remain pretty much the same in any universe. Now, if your mind is sent swimming at this point, there's a book you can read called Parallel Worlds that I wrote years ago, and it explains all the incredible developments once you assume that atomic physics has to apply to the Big Bang, necessitating a multiverse of universes. So get a copy of my book, Parallel Worlds. Okay, let's move on to the next listener phone call.
Hey, this is Armand from Queens, and I was wondering, Ray Kurzweil thinks that the singularity is going to happen around 2030. What do you think? I believe, personally, that it's going to happen a little earlier because of the way technology is expanding. And by singularity, I mean like where we bind with machines and you can have like almost immortality. I think it'll happen around 2025, but what do you think? Have a great one. Your show's awesome. Peace.
Okay, well, let's talk about the singularity. First of all, Ray Kurzweil is a friend of mine. I've interviewed him several times for the Science Channel and also for Science Fantastic. That's right. We've had Ray several times on radio. And Ray now works for Google. He's one of the Imagineers of Google, thinking about what the world will look like in the coming decades. And his book is called The Singularity is Near. And what is a singularity? First of all, the word comes from physics. My physics, that is black hole physics. And so we think that at the center of a black hole, there's a rip in the fabric of space-time called a singularity. However, the singularity when applied to computers is the point where, well, depending upon how you define it, when machines become smarter than humans. Now, there are many ways to define singularity. One way is to simply say the humans are simply outdistanced by robots. The robots become smarter than us. Another definition is that robots have children, which are smarter than them. They have kids, grandkids, which are even smarter than them. And this process goes on very fast until the robots take over. The robots take over not just the Earth, but they take over the solar system. They begin to cannibalize atoms of the Earth to create computers, gigantic computers the size of the Earth. And eventually they eat up the stars. And eventually they eat up the galaxies. So what about that singularity? Well, let's take a short commercial break. And after the break, we're going to talk about what happens when the robots become smarter than us. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we go right to the cutting edge of science, right to the point where science, in fact, begins to meet science fiction. Well, before the break, we had a question about the singularity, and there are many definitions of it. One definition of the singularity is when robots become smarter than us. Another definition of the singularity is what happens when robots beget other robots, each one smarter than the previous one, and it goes on forever. And then the robots take over, not just humanity, they take over the Earth. They take over the solar system. In fact, I once interviewed Ray Kurzweil, who is a futurist with Google, and he mentioned that when he looks at the stars at night, he sometimes wonders, out there, with so many stars, maybe one of those stars has a planet which has reached the singularity already, and perhaps they're already engineering their solar system. Perhaps they're moving planets, moving stars around. I mean, the mind starts to boggle thinking about what happens when intelligence can go haywire and become infinitely powerful. Think about that. Well, then the question was, how real are any of these scenarios? Well, first of all, let me point out that Moore's Law, which simply says a computer power doubles every 18 months, is slowing down. So all the wonders of technology that we enjoy today are not happening on schedule anymore, because we're now making transistors the size of molecules, and the age of silicon can come to an end. And a lot of these calculations of the singularity are based on extrapolating Moore's Law into the future. Now, that doesn't mean that we cannot replace silicon with molecular computers, quantum computers, atomic computers, DNA computers, protein computers, and optical computers. The problem is we don't have them yet. And so at the present time, we don't know if Moore's Law is going to continue, and therefore that adds a certain amount of uncertainty as to when the robots are going to become smarter than us. I personally think that by the end of the century, perhaps we'll have machines that can compute faster than us, that begin to rival human intelligence, that have self-awareness. Now, once robots have self-awareness, they could become dangerous. Let's not be naive about this. Elon Musk has said that robots pose an existential threat to humanity. Well, I think for the coming decades, I think Zuckerberg is right. Artificial intelligence will give us jobs, economic growth, activity, billion-dollar corporations. In other words, a new renaissance. However, in the century, robots could become self-aware. At that point, I think we should put a chip in their brain to shut them off if they have murderous thoughts. But then some people say to me, Professor, let's not be naive. I mean, at a certain point, the robots are not stupid. They'll figure out that we have a fail-safe system, and they'll simply remove it and continue to become super smart. Then, smarty pants, what happens to us? Well, at that point, I think we should, and this is again over a century from now, I think we should merge with them. Why fight it? Merge with them. That is, become superhuman. Become Superman and Superwoman with superpowers. They'll look just like us, except they'll have superhuman abilities, and they will be our future. Okay, let's take another short commercial break. Once again, this is Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question about the singularity. And as I mentioned, we don't know when the singularity is going to happen. First of all, I think that something like that will actually happen. Robots are getting smarter, even though Moore's Law is slowing down. Computer power, by the way, is slowing down now. We're beginning to reach the end of the age of silicon. But time marches on. And it does mean, I think, that one day we'll have machines that can compute as fast as us. And going even beyond that, one day we'll have machines that are self-aware. Now, if you look at the animal kingdom, we see that our most advanced robots are as smart as a cockroach. A cockroach, you can put a cockroach in the middle of a forest. The cockroach can find mates, food, shelter, hide. Cockroaches do very well in the forest. If you put our most advanced robot in the forest, what does it do? It gets lost. That's how primitive our robots are. But let's not be naive. Perhaps by the end of the century, they'll become smarter, perhaps as smart as a mouse, as smart as a rat, as smart as a rabbit, as smart as a cat, dog, and then as smart as a monkey. And at that point, they could become dangerous. At that point, I think we should seriously put a fail-safe system so that we shut them off if they have murderous thoughts. And beyond that, now I'm talking about the 22nd century, I think we should merge with them. Now, some people say, I don't like that idea. Does that mean my brain is going to be put into a vat of liquid connected to a mainframe computer? I mean, how boring. Does that mean I'll spend all my days trapped inside a computer? Incredibly boring. Well, no. If you are inside a mainframe computer, it means that you can control an avatar. A mechanical avatar that sends messages to the mainframe so you literally think and feel as if you are that avatar. And that mechanical avatar is a Superman, a Superwoman, beautiful, handsome, super strong, can live on Mars, live on Jupiter, live anywhere it wants to live, and explore the universe. Think about that. Our future could be to merge with our creations. And it's not so grotesque as some people believe, because one day you could wind up waking up as Superman and Superwoman. Okay, let's move on to the next listener phone call.
Hey, this is Brandon from Manhattan, and I was wondering, they were supposed to do a head transplant back in December. Do you have any updates on that? Do you know about the scientists that are doing that? And do you believe it's possible to do a human head transplant? Because that's what they were doing. The guy was paralyzed and he wanted to put his head on another body. Just let us know about that science. And have a good day. Your show is great.
Okay, well, I haven't heard about that, but I personally think that it's not possible with today's technology to do a head transplant. For the simple reason that the number of neural connections in the spinal cord is astronomically large. And these nerve connections are the size of nerve fibers and molecules. And so we're talking about a fantastic degree of surgery, microsurgery, that is way beyond anything we can do. We can barely hook two ordinary neurons together using robots. And think about it, connecting thousands, millions of these neurons that exist inside the spinal cord. And so, well, in science fiction, it's always a great idea. But I think in practice, it's something that is way beyond our technology. Now, face transplants have already been done, and maybe that's what you're referring to. But a transplant with regards to the entire head is far beyond anything of our technology of today. We don't even have a map, a road map of the various neurons of the spinal cord, so we don't know what is connected to another. For an example, think of a cable connecting Manhattan to the rest of the world. That cable can be cut, and can you splice it together? Not anytime soon. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we take any and all questions about science, even goofy ones, questions which seem to be rather outlandish, because you deserve a straightforward answer from a scientist. Okay, let's move on now to the next listener phone call.
Hi, my name is Roger. I'm listening to you on 1450 KBKW. My question was, as DNA came into place, can people clone other humans yet, or have humans been cloned throughout the world? Maybe we just don't know about it yet. But I was thinking with DNA, for sure, it has been done already. That's my question. Thank you.
Okay, that's a valid question. The answer to your question is so far, no. However, it is inevitable that at some point or other it will happen. So let me back up a bit. First of all of us are made out of DNA, which is the code of life. One molecule of DNA contains all the information and principle necessary to create a copy of you. DNA makes copies of itself all the time, and that's why we can live. And then the question is, what happens if we artificially make a copy of the DNA, and that is called cloning. So a clone is a genetic twin, not made by a mother, but a genetic twin using biotechnology. Now, as you know, it's commercially available now. We can clone pets, dogs, cats, even horses. We can clone household pets and animals, and people have done that. We all hear about stories of some celebrity that lost a cherished dog or a cat and wants to bring it back to life. Well, of course, you're not really bringing back the original. The memories are all different. However, the genetics are roughly the same. You're talking about a clone. Now, have we cloned monkeys, primates? And the answer is no. At the present time, we have cloned farm animals, we've cloned pets, but we have not yet cloned a primate or a monkey. And that means certainly we have not yet cloned a human. Now, does that mean that we haven't cloned individual cells of humans? And every once in a while in the media, you hear that scientists have been successful to clone individual cells of humans, in some sense playing God, but not creating a clone that looks like you and me. That has not yet been done. Will it be done eventually? I think yes. Originally, even the Catholic Church railed against cloning, but I think one day it'll be accepted. It's inevitable, and it's not going to be such a big deal. I mean, after all, who's going to be cloning? Rich people who have no heirs, or rich people who have no heirs they particularly care for. They'll want to clone themselves and give their money to themselves as children to start all over again. So I think the usefulness of human cloning is going to be rather limited. Not everyone is going to want to clone. Okay, let's move on now to the next listener phone call.
My name's Tim Barnett. I live in Shelton, Washington. But my question would be, how do we warm ourselves with all the technology with a cheap and easy way other than wood that our caveman ancestors warmed themselves with? All right, thanks.
Well, you asked the $64,000 question as to what is going to be the energy supply of the future. Our ancestors, of course, discovered fire. That was one of the pivotal events in human history. And what did we burn? We burned wood. And that opened up civilization as we know it thousands of years ago. Well, today we're reaching yet another milestone. We went from wood to things like coal and charcoal and now oil. And beyond that, what are we looking at? Well, beyond that, we're looking at variations of hydrogen power. First of all, solar and wind. Why don't we have solar and wind power? Why is it that only Hollywood millionaires have gigantic, beautiful, gorgeous solar and wind-powered homes, but not the average Joe and Jane? Well, because of inefficiency. It turns out that solar and wind are not that efficient. What happens when the sun doesn't shine and the winds don't blow? That's where the battery comes in. The bottleneck in terms of creating cheap and renewable energy sources is the battery. But battery power is getting cheaper every year at 7% per year. And it does mean that with super batteries being created, it does mean that one day solar and wind power will become fully economical and competitive. And then there's the dark horse, and that is fusion power. We physicists are betting the store on fusion, but to be honest, every year we push the date of fusion back. And if you want to find out more about fusion, then go to the web, type ITER. And the ITER is the initials for this thermonuclear reactor being built in southern France. Is bankrolled by the United States, the European Union, Russia, Korea, Japan, and, of course, many European nations. And one day it will replace oil and coal, but not yet. When would it happen? As I mentioned, perhaps around 2050. So don't hold your breath. Fusion power is the future, but perhaps it's not the future for us. Perhaps the next generation will have the benefits of fusion power. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing the world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Let's move on now to the next listener phone call.
Earl Smith, listening to KEYF in Corpus Christi, Texas. I have a question. I understand that on a number line between, say, number 1 and number 2, there are an infinite number of points. But how is it that I can arrange my finger to be 90 degrees to the number line, and I can run my finger across that line and pass over each one of those points? Thank you.
Well, you ask a variation of the Zeno paradox, which is literally 2,000 years old. Zeno, the great Greek philosopher, had a proof. And the proof was that motion was impossible. That's right, nothing can move. And he proved it exactly the way you mentioned. If I take a river and I mark 2 points on it, the beginning and on one side of the river to the end of the river, and then I ask a simple question, how long does it take to go between 2 points? You realize that there are an infinite number of points between point A and point B, and it takes an infinite amount of time to go through an infinite number of points. Therefore, said Zeno, nothing can move. Motion itself, he said, was impossible because it takes an infinite amount of time to pass through an infinite number of points. Ergo, motion was impossible. Well, on one hand, people thought he was nuts. I mean, what? Of course things can move. But if you think about it, how many points are there between points A and B? And then you begin to realize, hey, this is really a deep question. And it was finally solved by people like Isaac Newton and the mathematicians of the 17 and 1800s when they invented calculus. They showed that it takes a finite amount of time to move through an infinite number of points if you very carefully divide up the interval and take the limits correctly. And so this is the beginning of calculus, which on one hand seems impossible because you are talking about dividing up a point into an infinite number of intervals, and motion, which obviously exists. I mean, things obviously move. Any idiot knows that. But if you think about it, what is the smallest distance? Well, today we have a more modern view of that question, and that is, what is the smallest distance between 2 points? We once thought it was the atom, that the atom was the smallest object, and therefore the atom was the smallest distance that you could make between 2 points. But now we split the atom. We have now protons and neutrons, which are even smaller than an atom. And now we can even bust up the protons into quarks. And so we're back to Zeno's paradox again after 2,000 years. What is, therefore, the smallest distance? Well, we're not sure. But many physicists believe that the smallest distance is the size of a string. The string is extremely small, 10 to the minus 33 centimeters, is the smallest distance that has ever entered the annals of physics. And we think that that is the smallest distance of all. And that, therefore, Zeno, in some sense, was onto something. He thought this went on forever. But we physicists think, no, it stops. We're not sure, but we think it stopped at the size of a string. And if you want to know more about string theory, get a copy of one of my earlier books, Hyperspace, which talks about vibrating strings in 10 and 11-dimensional hyperspace. We think that is a theory that eluded Einstein, because Einstein wanted a theory that would allow him to, quote, read the mind of God. So find out more about this by getting a copy of my earlier book, Hyperspace. Okay, let's move on now to the next listener phone call.
This is Denise Miller, and I'm calling from Corpus Christi, Texas. And the station that I'm listening to is KEYS Radio. And I've listened to you many times before when you were at 4 o'clock in the afternoon. And I just want to tell you, even if I'm not able to get on to speak to you, I really have enjoyed your program. You're a real thought provoker. My question is, with all this robotic stuff, where does faith and religion and feelings come in? Thank you. This is Denise Miller.
Well, you asked one of the big questions, and that is, what is the relationship between humans and robots as we go into the future? Are robots going to be unfeeling? Are we going to become more robotic? What is the relationship when robots gradually approach human intelligence? Well, first of all, let me give you a time frame. Robots today have the intelligence and emotional ability of a cockroach. So don't expect robots to replace us anytime soon. However, let's take a short commercial break. And after the break, we'll talk about robots that can feel, robots that have emotions. And what does it mean when one day robots can be emotional just like Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science. And before the break, we had a question from a listener asking about, well, what happens when robots gradually become like us? And then the question is, what about emotions and feelings? And how close can robots come close to us? Well, first of all, there is such a thing as a science of emotions. At MIT, for example, at the Artificial Intelligence Laboratory, they're trying to create emotional robots. Now, you may say to yourself, Why? Why would anyone want to create a robot that can cry or laugh? Well, first of all, some of these robots already have a practical application, and that is they're used in nursing homes where people get lonely and need a companion, and they want to talk to something. Of course, you can't have a caretaker there 24 hours a day. However, emotional robots are one pioneering area that MIT scientists are looking into. First of all, it's rather easy to simply understand the emotions of the face. Face recognition technology already has given us the ability to identify anger and puzzlement and things like that in the human face. That's not the problem. Also, we can mimic the muscles of the human face to mimic fear and mimic joy and things like that. That's not the problem either. The problem is to figure out when things are appropriate. Because if you give the wrong emotion for a certain situation, people get insulted. They get angry. If, for example, you're grieving because a relative died, and here's this wiseacre robot laughing and joking, you get insulted. And so it's much more complicated to figure out when certain emotions are to be required and when certain emotions are not to be used. But again, the first application is in places where we have loneliness. And we also see them in Japan. In Japan, where we have an aging population, and also at MIT, where we have experiments done on nursing homes, we find that these emotional robots are actually quite good, that they do give a sense of companionship to people who are normally lonely and cannot afford to have 24-hour care. That, of course, is not the real thing, but it's better than nothing. And as time goes by, we'll have robots that are more and more accurate in terms of their understanding the emotional state of another person. Now, if you watch Star Trek, there is Data, the robot that wants to become human. And we find that things are done inappropriately. Data laughs at the wrong points, misunderstands simple human behaviors, and it's going to take time. But it's not out of the question. The difficult thing is to figure out when certain emotions are appropriate and when certain emotions are not appropriate. And then the next question is, can the robots really feel this thing, or is it simply mimicking, like a tape recorder, an emotion? In other words, if a robot seems to cry, is the robot really crying because it feels bad, or is it simply pushing a button that says, time to cry? Well, I think the two are quite different today because our technology is quite primitive. But as time goes by, in the future, the two will become indistinguishable. That is, robots which can push the button which says, time to cry, and actually, quote, feeling crying, feeling sadness, will become closer and closer with time, so that for all intents and purposes, we will be able to interact with robots that feel sad. Now, I should also point out that there's something called the uncanny valley. Now, let's say that you get a robot that is emotional, but it's not quite there, doesn't quite look human, but tries to be human, and makes emotions that are slightly inappropriate. What do? You get the creeps. You say, this is really creepy. For example, think of Halloween. During Halloween, what do you have? Inappropriate emotions. You see ghouls and monsters smiling at you, and it freaks us out. We feel really creepy seeing somebody that is obviously a monster grinning and smiling at us. So inappropriate emotions make our skin crawl. And this is called the uncanny valley. If a robot is quite unhuman looking, we can look at it, laugh at it, and analyze it. But as it becomes more and more human-like, and still makes slight mistakes and is not quite looking human, we get a creepy feeling, and that's called the uncanny valley. And then, of course, when the robot has perfect emotions and perfect feeling, then we accept it as a sentient being. But before then, we get the creeps. And, of course, at Halloween, many people who make Halloween masks know this, inappropriate emotions. And that's going to be a problem for robots for quite a while to get the emotions right. For example, one scientist pointed out to me that if you have a father with a towel slapping the butt of a son, on one hand, the son could say, "Oh, my father is being playful," and the son will start to laugh when the father whips a towel at the son's butt. But if it hurts, and the father starts to grin in a bad way, then the son starts to cry because he knows that it was meant as punishment. So the slightest difference in a person's facial expression can signal the difference between happiness and sadness. And at the present time, robots are far from being able to master these simple emotions. Okay, let's move on to the next listener phone call.
Paul Kruger, Interlochen, Florida. I'm just responding to a tweet. This is the question. In the search for dark matter and dark energy, is there a possible link between these and primordial antimatter? What became of the energy released when said antimatter was annihilated by matter at the time of the Big Bang? And could that be related to dark stuff?
Well, you ask a question for which there's no simple answer, but first of all, let's define the terms. Dark matter, we know exists, but it's invisible. And we have maps of dark matter, but no one's ever seen dark matter on the planet Earth. Therefore, it's one of the most mysterious of all substances, but ironically enough, it makes up most of the universe. Most of the matter, by a factor of 10, most of the matter in the universe is actually not ordinary matter at all. Is dark matter. Then there's dark energy, which is the energy of the vacuum. It is also invisible, and it is responsible for pushing the galaxies apart, and that's called the Big Bang. So you got that? Dark matter surrounds the galaxy, holds the galaxy together, is invisible, but is ordinary matter. Then we have dark energy, which is energy that is pushing the galaxies apart, and that is causing the expansion of the universe. Then, if that's not complicated enough, we have antimatter. Now, antimatter already exists. It was postulated around 1928 by physicist Paul Dirac, and he realized that Einstein's equation E equals mc squared was not quite right. When you take the equation E equals mc squared, which even children know, you have to take a square root. And therefore, it's actually E equals plus or minus mc squared. I repeat, Einstein's famous equation is actually slightly wrong. Einstein, of course, knew this. The correct equation is E equals plus or minus mc squared, but the minus was once thought to be rather useless. I mean, who needs negative matter, right? Well, this is where antimatter comes in, because then Dirac stated that, well, you just can't throw away the minus sign. It has a role to play, and that is antimatter. Now, antimatter is visible. We don't know what it looks like, but if you had enough of it, it should look like ordinary matter. It has all the electrical properties of ordinary matter, and so we think if you have anti-atoms, you can eventually create anti-molecules, and eventually anti-objects and anti-people. That's right. We think we can create people made out of antimatter. Of course, we haven't done that. We've only made tiny snippets of antimatter in the laboratory. In fact, when I was in high school, I played with antimatter for my science fair project. So then the question is there a relationship between all three? First of all, antimatter is not dark matter. We can rule that out right now, because dark matter does not have charge. Antimatter does. And so we can rule that out immediately. But what about dark matter and dark energy? The short answer is we don't know. However, let's take a short commercial break, and after the break, I'll give you the leading theory about what dark matter is. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. You're not going to get a busy signal. You'll get right to us. Before the break, we had a quick question about three things: dark matter, dark energy, and antimatter. What's the relationship between all three? First of all, antimatter exists. We create beams of antimatter at the Large Hadron Collider outside Geneva, Switzerland. So antimatter is not the mystery that it used to be decades ago. In fact, on Star Trek, it is absolutely true that maybe one day we'll have antimatter engines. Not at the present time. Antimatter is extremely expensive to make. It would cost trillions of dollars to make even a few grams of antimatter. So antimatter is not so mysterious. But dark energy is mysterious. We simply don't know what dark matter and dark energy are. Dark matter holds the galaxy together, so we know how important it is. Without dark matter, our galaxy would have flung apart billions of years ago. The leading theory of dark matter, which is not proven, the leading theory is that it's a higher octave of the string, that we are the lowest vibration of tiny vibrating strings. The universe is a symphony of strings, and we just happen to be the lowest octave. However, everybody knows there are other octaves out there, higher notes. And these higher notes have names. One of them is the photino, and the photino is, in fact, the leading candidate for dark matter. So we think that dark matter is ordinary matter vibrating at a much different frequency, and the frequency given by string theory. And if you want to know more about this, get a copy of my book, Parallel Worlds, where I talk about dark matter and string theory. Okay, let's move on to the next listener phone call.
Hello, Dr. Kaku. My name is Albert. I'm in San Jose, California, and I listen to you on YouTube. First of all, as always, I think it's a great honor to be able to ask you a question. First of all, about parallel universes and time travel, I'm a little bit somewhat confused. I want to ask you something about this. Suppose you want to go back in time, that there's a method. Now, the steps involved in the method, how would you choose which parallel universe to go back into time to avoid the paradox? In other words, if you go back in one parallel universe that does not, maybe nature has somehow safeguarded, if I'm not, correct me if I'm not right, nature won't allow us to go back in time in this same universe, only in parallel universes to avoid the paradox. So I just wanted to clear that up a little bit. So yeah, if you go back in time, okay, and let's say you always had that little example of you met your mother and you fell in love with her and so forth and so on. I found it a little amusing. But it's true, though. Then there would not be any type of paradox, would it? Thank you. Have a great day. Thank you.
Okay. Well, welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about time travel. What happens if you go backwards in time and really mess up the past so that the present is not possible? The simplest time travel, which gives you a paradox, is you go backwards in time and meet yourself as a young kid, and then you kill him. What happens? You just committed suicide in the past, so how could you be born? How could you be alive to go backwards in time when you just killed yourself in the past? Or what happens if you go backwards in time and your mother falls in love with you before you're born? How can you be born if your father and mother never got together because you interfered? Well, the brain goes crazy thinking about these things, but let me summarize the state of affairs. First of all, Einstein thought that time is not a straight arrow like Newton thought, but more like a river which can bend and meander. And the new wrinkle that even Einstein realized is that the river of time can have forks in the river of time and whirlpools. If you have a whirlpool in the river of time, then time travel is possible, and all the paradoxes of time travel have to be taken very seriously. And then in 1949, Kurt Gödel, the famous mathematician, one of the greatest mathematicians of the millennia, came up with a solution of Einstein's equation which did allow for time travel. If the universe rotated and you were to go around the rotating universe, you'd go backwards in time. Einstein was disturbed. He was really disturbed because here was a solution which seemed to defy common sense, staring at him in the face. In Einstein's memoirs, he said that we can dismiss this for physical reasons, i.e., the universe does not rotate. The universe expands, as in the Big Bang, but it means that if the universe did rotate, then time travel would be commonplace. Well, Einstein thought that was an anomaly, but since then, we physicists have discovered scores of time travel solutions, which makes things embarrassing. In fact, we even give them a name, CTC, closed time-like curves. So if you want to know how a scientist views time travel, don't Google time travel. You'll get all the science fiction. Instead, Google CTC, or closed time-like curves, and you're going to find out how real physicists deal with time travel. Now, how do we deal with the paradoxes? There are several ways of dealing with the paradoxes. The first way is something I don't believe in, and that's been proposed by Professor Novikov of Russia. And he says when you go back in the past, things are self-consistent, so it was meant to be that way. You, in some sense, fulfill the past. It was meant to be that way, and there are no paradoxes. Well, personally, I find that really hard to believe, that if you go backwards in time and really mess things up, then it was meant to be that way, and so there are no paradoxes. I find it a little bit hard to believe that. I believe in the quantum theory, which simply says that you enter a parallel universe. In quantum mechanics, which is the leading theory of all matter, like atomic physics that we teach in graduate school, time can fork into two rivers. Each time a decision is made, the river of time forks into two rivers. These are called quantum events. And it simply means that if you go backwards in time, you enter a different time stream. So that when you save Abraham Lincoln from being assassinated at the Ford Theater, you're saving somebody else's Abraham Lincoln, not your own Abraham Lincoln. So there are no paradoxes. This means, of course, that there could be other parallel universes where things are messed up and things really are goofy, but that's a whole other question. So what does this have going for it? What it has going for it is that quantum mechanics, no matter how goofy it sounds, is really true. It really is the way things are. That our brain, which is classical and Newtonian, our brain which believes that everything happens in definite states, that the past is the past and the future is the future, well, that's wrong. There are apparently other parallel universes. And then the last question that everyone asks is, can you go between universes? That is, if you go backwards in time, and let's say you wind up in a universe that you don't like, can you go backwards again and enter a different universe? Or let's say in one universe, a loved one is alive, in another parallel universe, a loved one is dead. Then the question is it possible to go between universes to bring back the dead? Well, it turns out that in principle, quantum mechanics does allow you to go between universes, but it is astronomically difficult. Don't expect anyone to do that anytime soon. In other words, it takes an energy of a black hole, fantastic energy, to do this. And it's not going to happen anytime soon. But let's take a short commercial break, and after the break, we'll get more into traveling between parallel universes. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about time travel. What do physicists think about going backwards in time to perhaps a parallel universe? Would that allow you to solve all the time travel paradoxes, like what happens if you kill your parents before you're born? And the answer is yes. If you wind up on a different timeline, then you killed your parents before you were born. Then it turns out that the people that you just killed look like your parents, have the same genes as your parents, but are actually copies of your parents in a parallel universe. That's how we get around all the time travel paradoxes. So take any movie that you've seen about time travel, and draw a timeline, and you can see how the timeline splits and breaks apart, but you can graph exactly what happens each time you enter the time machine. So there are no paradoxes. And then the last question is, can you move between parallel universes? In principle, the answer is yes, but to open up a parallel universe requires enormous amounts of energy comparable to a black hole. So don't think that any inventor is going to create a black hole and a time machine in their basement. It's not going to happen anytime soon. Now, some people think maybe there's a loophole there, because it turns out if you look at Einstein's equations very carefully, it depends on the speed of light. Therefore, if you could alter the speed of light, then the amount of energy necessary to build a time machine can be made smaller. In fact, there are some people who say, aha, that's the loophole in Einstein's equations which allow for time travel. Change the speed of light, which you can do in the laboratory. Well, not so fast. It turns out that in the laboratory, yeah, you can slow down time, but it's an illusion. In fact, I once took a film crew to Harvard University where we filmed this effect. We actually filmed the effect of light slowing down. Now, how does that work? Light in a vacuum always travels at the speed of light. So between two atoms, light is traveling at the speed of light. But when it hits an atom, it gets absorbed, and then a fraction of a second later, it's shot out again with a time delay. So the time delay gives you the illusion that light has slowed down. It hasn't slowed down at all. Between atoms, the speed of light is the speed of light. But because it hits an atom and is absorbed and then re-radiates a split second later, there's a delay time. For example, think of the early Pony Express. Remember way back in the 1800s, before telegraph wires came in? People would get on horses and ride horses between point A and point B. Once they went to point B, they would rest, get on another horse, and then shoot again to point C. Well, of course, between outposts, you were traveling at the speed of a horse. But the average velocity was much less, giving you the illusion that the speed of the horse was less than it really is. So that's how the so-called loophole in Einstein's equations is not a loophole at all. In other words, to sum up, sorry about that, time travel still is extremely hard to perform, requiring energies comparable to a black hole. And we can barely control the energy of a furnace, let alone the power of a star or even that of a black hole. Sorry about that. Okay, let's move on to the next listener phone call.
My name is Chris Nelson. I'm calling from Toronto, Ontario. I have a question. During the last post-extinction of mankind 70,000 years ago, is it possible that we were evolved enough and smart enough at that time to build the pyramids, to have built Atlantis, to actually had the vehicles that had flight, that we actually carved all the lines in Peru? That's my question. I'll wait for your answer. Thank you.
Okay, well, you ask a very interesting question. Let's break it down into its components. Yes, first of all, 70,000 years ago, roughly speaking, something happened that was catastrophic that killed off most humans. By looking at the DNA, you can recreate a genetic map of the human race showing that there is a pyramid, and at the tip of the pyramid is when early humans regenerated the entire human race. Something wiped out almost the entire human race, leaving only, a few hundred, maybe 1,000 people to repopulate the entire earth. Some catastrophe happened, and if you go to the geological history books, there was something catastrophic 70,000 or so years ago, and that was the eruption of the Toba volcano. in Indonesia, which blanketed Africa with soot, changed the weather, destroyed much of the life and vegetation in Africa. And we think that's the reason why only a handful of us, a few hundred of us, survived to repopulate the entire human race. Now, that was about 70,000 years ago when it was still in the Ice Age. Then, 10,000 years ago, something magical happened. Because before then, we were still savages. We operated in small tribes of maybe 100, 200 people. We were scavengers in the ice. It was a hard living. Cities did not exist because, of course, if the buffalo left, if the antelope left, and you were still there in a city, you'd starve to death. You followed the game. This was before farming. As a consequence, we lived in small pockets with no accumulated technology. The technology necessary to cut stone and to create advanced tools and clothing did not exist because we had to carry on your back everything that you owned. We were nomads. Nomads going between point A and point B, desperately trying to find food. Then the ice melted 10,000 years ago. Then we started to get cities and accumulate knowledge, which then gave us about 5,000 or so years ago, the pyramids. And so the technology of the ancients, talking about Atlantis and cities and stuff like that, that's recent on a scale of maybe 4,000 to 5,000 years, but the extinction event was 70,000 years ago. Okay, well, unfortunately, that's it for Science Fantastic.